Okay, so today we're going to begin a new topic that is the Laplace Transform. The Laplace Transform is probably one of the most useful, probably the second most useful thing that you're going to learn in this course that you're going to be using forever, only after the Fourier Transform. Laplace Transform is extremely helpful. So here we will see that it will allow us to solve arbitrary equations. Many times we're going to solve equations with non-constant coefficients, equations even with some nonlinearities and things like that. It's going to be really, really powerful to solve differential equations. But not only that, you're going to be using it in circuits all the time. Oftentimes you use Laplace Transform to solve circuits, and you will hear that you go from the time domain to the frequency domain. I mean, we will learn that actually the Laplace S domain is not really the frequency domain, even though in engineering oftentimes it's called that. For the frequency domain, if you are in time domain, go to the frequency domain would be a Fourier transform, actually, could I say. But anyways, just telling you that it's something that you will see everywhere. It's super interesting. And it's your first steps into a little bit more advanced math than what we've seen so far. Slowly, let's see if we can learn and we can get used to the language in which we talk. Because once you learn these things, you will remember. It's like riding a bike. Laplace transforming is like riding a bike. Once you learn it, it's going to be there forever. All right, let's begin. So what is the Laplace transform? Well, the Laplace transform, I wrote here, is a linear integral transformation that takes a function f of t as an input and returns an output, a function capital F of x. You see what I mean? T domain, S domain, we're going to use that terminology is often used in engineering. So I'm going to call that if this is the time domain, this will be the S domain, T domain, S domain. Okay, that's a way in which we will call the two functions in terms of the dependence on what variable. Now, this symbol is a calligraphic L, and it's telling you that the calligraphic L represents the Laplace transform with a curly bracket, and then inside the input, which is f of t in this case. Now, the definition is this one. It's defined through an integral. So it's really important that we start learning about, because there are typical mistakes that engineering students make that we should avoid. They're really, really bad ones. If you see an integral like that, so you see L of f is defined through an integral. So you put the L, so you basically is, you would have the Laplace transform is like, okay, take this integral, 0 to infinity e minus st dt, and put here the function you want to transform. That's what it is. Now, super important. How many t variables are there on this line? How many s variables? Well, s variable is 1, f of s, and the s is here, dependence on s, you see? And then how many t variables are there? The right answer is 0. What do I mean? What do you mean 0? There's a t here and here. No. This t is integrated over. So super important. If I have a function f of x, y, and I integrate over y, right? Whatever domain, I don't care. I mean, I don't write 0 to infinity, but I could write anything. AB, I'm going to write AB. AB. This thing is a function of only x. It's no longer a function of y. Y is being integrated over. It's what we call a dummy variable. Get that name in your mind. This is a dummy variable. And what does that mean? That means that I can call it Joshua if I want. If I change y and I call it J, and J here, it's the same freaking result and nothing changes. It's never dependent on y. Y is integrated over. And I can call it J, I can call it whatever. It seems very easy because you say, well, it's a trivial substitution. People make a lot of mistakes with that. When we start seeing more complicated theorems, we have to make changes of variables and rename things. People get confused with dummy variables. So keep in mind, once a variable is integrated over, there's no dependence on t. In this line, nothing depends on t. Nothing. T is integrated over, you see? The whole line depends only on s. All right, well, this thing depends on t inside, but it's integrated over. Okay, so t is a dummy variable here. All right, hopefully that's clear. Now, you can tell the definition is this improper integral. So, to find the Laplace transform, so maybe you were thinking right now, yeah, I'm going to have to integrate a lot of those. Well, sometimes yes, but we're going to learn some rules because we're going to prove what are the Laplace transforms of basic functions, and out of that we're going to be building the Laplace transform of more complicated ones through some theorems that we're going to prove. So anyway, the beginning of the topic of the Laplace transform, before doing examples, 1,000 examples and solving exercise and so on, it's going to be more abstract. But abstract thinking is the kind of thing that develops minds, okay, and open them to new fields. So be prepared for a little bit of that kind of action. All right, so the first thing that we realize is, well, this Laplace transform, for it to exist, this integral has to exist. It cannot be divergent, right? So not every f of t will have a Laplace transform for all values of s, right? There will be a domain in which it exists, all right? The domain that we can call it a radius of convergence. But in this course, we're not going to care that much about the convergence of the Laplace transform. We're going to care about computing Laplace transforms when we can compute them. But just so you know that this integral not always exists. And then there are ways to make it work even when it no longer exists, but that is beyond the scope of the course. So what I'm going to tell you is that there's way more that hopefully those of you that really like signal processing and information theory will get to learn more. But for now, let's focus on what we have at hand. Let's learn how to compute these kind of transforms, shall we? Let's make one observation. I say it's linear. Is it really? Well, yes. It's very easy to prove, and prove it because the integral is linear. So the Laplace transform of alpha f of t plus beta g of t, it's equal to the Laplace transform of alpha f of t plus the Laplace transform of beta g of t. All right? And then why? Because the integral of a sum, the integral of f plus g dt is equal to the integral of f dt plus integral of g dt. Because the integral is linear, the Laplace transform is linear. But then again, the integral also, constant factors can come out of integrals. So this is also alpha Laplace transform of f of t plus beta Laplace transform of g of t. Or in other words, we can even say alpha capital F of s, write an explicit little dependence, and beta capital G of x, where alpha and beta are real numbers in here. So yeah, the Laplace transform is linear. Another notation we're going to learn is what is the symbol that we do when we undo the Laplace transform. So the inverse Laplace transform. The inverse Laplace transform, we will notate it with L minus 1. Well, L minus 1 works like this. If I get f of s and I do the inverse Laplace of f of s, this thing is the inverse Laplace of the Laplace of f of t, right? These two things cancel, and what we have is f of t. Basically, the inverse Laplace transform, we notate it with an L minus 1. Okay, that means untransform. Go back. If the Laplace transform takes you from f of t to f of s, the inverse takes you from f of s to f of t. All right, so let's begin computing some cases. Let's compute the Laplace transform of basic functions, shall we? All right, let's compute the Laplace transform of a constant. But before doing that, let's recall what the Heaviside step function is. Oftentimes people read that as, oh, this guy puts an h in a circle. It's not an h in a circle. It's capital theta. So this is theta, and what I call capital theta, I write it like this. All right? So it's capital theta, not an h in a circle. In any case, the Heaviside function sometimes is notated with capital H, but that's a bad idea for reasons that we will see later. I would not call it that. I'm going to use capital theta, okay, of t. The Heaviside function is just if you want a function that is 0 when t is less than 0, and 1 when t is larger than 0. Now, I define it here with t larger or equal than 0 is 1. We will learn, when we actually learn Fourier series, that maybe the better way to define that is giving it the value of 1/2 when it's 0. When t is equal to 0, making it 1/2, just in the middle of the two. Why? We will learn later, okay? But for now, let's just use the more standard definition, that is 0 for the negatives, 1 for the positives, and 0, okay? Now, of course, if I write the Heaviside of t minus a, what is that? Well, if I subtract from the argument something, I'm displacing the function to the right? So this argument will be negative until t is equal to a, and then positive after t is larger than a. So this displaces the Heaviside to the right. In fact, subtracting some value, some constant value from the argument of a function, displaces it to the right, and summing it, displaces it to the left, if a is positive. Alright, just a little reminder. Now, why am I reminding you of this? Because of something interesting. Notice that when I'm transforming Laplace transform in a function, f of s, capital F of s, the Laplace transform does not care about what happens with the negative values of t. Whatever the function does to the left of the y-axis, the Laplace transform doesn't care. You see, it doesn't influence. So if I have a function that is like Heaviside, like this, or a different function, imagine that instead of the Heaviside, I get a function that does It doesn't care. It will have the same Laplace transform because the Laplace transform starts integrating from here on. It ignores the negatives. So in fact, when we transform a function, Laplace transform will be exactly equal. The Laplace transform of the Heaviside times any function f of t is going to be the same as the Laplace transform of just the function. Because the Heaviside does nothing because it's 1, it's just I can substitute it for a 1 if t is positive, and I'm integrating over all the positives t. So it's really important to remember that the Laplace transform of a function and Laplace transform of a function multiplied by Heaviside is the same. This is the notion of something called causal functions in engineering, functions that are 0 before t equals 0. But for now, it's just good to remember, to have it in mind. Okay? So that's done. The Laplace transform of a constant, it will be the same as the Laplace transform of the Heaviside multiplied by a constant. Okay? Alright, let's erase the board and compute it. Alright, so let's compute the Laplace transform of a constant function. And remember that it's going to be the same as the Laplace transform of a constant function times the Heaviside, which means it's constant for t larger than 0 and 0 for negative t. Okay? So let's compute that. The Laplace transform of a constant times the Heaviside function is, of course, the integral from 0 to infinity e to the minus st. Put the function here. Let's write the constant outside, t dt, because the constant can come out of the integral. But of course, this is integrating over the positive numbers. For the positive numbers, this is the same as the integral 0 to infinity e minus st, or with the constant, of course, dt. Notice that if I had written the Laplace transform of just the constant, which is the same as a constant times the Laplace transform of 1, because of linearity I can take the constant out, this would have been the constant c, integral 0 to infinity e to the minus st dt, and you can tell they coincide, it's exactly the same, which is what I was telling you. The Laplace transform ignores everything that happens in the negative domain. Alright, that clarifies, it's the same thing. So I can write here a Laplace transform of a constant is equal to that. It's the same thing. Alright, so we have this integral to solve. But that's an easy one, it's an exponential. And remember how we treat improper integrals. So this improper integral, we understand this as a limit. So this is c, the limit when, let's call it w, which is what I would call it in the notes. W goes to infinity of the integral 0 to w e minus st dt. And this is just an exponential, so it's very easy to integrate. And we get that this thing is c, then 1 minus s, limit, that comes from the integral of the exponential, limit w going to infinity of e to the minus s w minus 1. Alright, so it's integral, so e to the minus st evaluated at the limits 0 w. Okay, at 0 gives me a 1, and at w gives me e to the minus sw. And of course, when we take that limit, if s is a positive number, then when this w goes to 0, this vanishes in the limit. So what I'm left with is c divided by s. And of course, this s has to be larger than 0. All right, so we see that this is the domain of existence, radius of convergence, if you want. But then we have the result, the Laplace transform. The Laplace transform of a constant, it's equal to the constant divided by s. Now that means, of course, this is the result, the first result we proved, is 1 over s. The Laplace transform of a constant is the constant times 1 over s. In other words, that also means the Laplace transform of 1 is 1 over s, which also means that the Laplace transform of the heavy side of t is, guess what, 1 over s as well, because it's the same as 1 for the Laplace transform. That clear? Alright, so we got the Laplace transform of a constant and the Laplace transform of the heavy side, which is basically the same. Alright, so we know what is the Laplace transform of a constant now. That also means, by the way, that the inverse Laplace transform of 1 over s is gonna be, well, take the inverse Laplace on both sides of this. So if I take the inverse Laplace of the left-hand side now, it's gonna be, this is heavy side, right? What have I done? I just take L minus 1 on both sides and wrote the sides the other way. So L minus 1 of 1 over s, this one, equals L minus 1 of L, the left-hand side, heavy side. Well, the L minus 1 cancels the L, and that means that L minus 1 of 1 over s, it's equal to the heavy side of t. All right? This is important to remember as well. All right, wonderful. So we know how to do the Laplace transform of the heavy side, or of a constant, which is the same, and how to do the inverse Laplace transform. And the inverse Laplace transform of 1 over s, we learned the inverse Laplace transform of 1 over s, and that's the heavy side. Our convention for inverse Laplace transform is always going to be that when it's a constant, we're going to ignore whatever happens on the left-hand side, is going to be the heavy side. Okay, so just taking inverses here. All right, if you have any questions about this, this is confusing, because you may be wondering, okay, hold on, why isn't it 1, right? Because if I do it here, yes, so you need to, when you do the inverse Laplace transform, you have to choose what happens with the negative part. Keep in mind the Laplace transform is not what we call unitary in a way. It doesn't, you lose information. When you move from the t domain to the s domain, you lost the information about what happens on the left of on the negative domain, the left of the y-axis, right? What happens for negative t is erased from the Laplace transform. So when you do the inverse Laplace transform, you need to choose what happens with it. And basically what we assume is that, well, when we do inverse Laplace transforms, what we know is that what we're going to assume, and it's a good assumption, and we will discuss why, is that the function is 0 until t equals 0. My t equals 0 is the origin of everything happening. If I have a signal and I use Laplace transform, I call time 0 to the beginning of that signal. There's nothing before that. That's kind of the assumption. It's very hand-wavy right now, but we will understand it as we go. We go. So important, the Laplace transform of the inverse Laplace transform of 1 over s is the heavy side, and the Laplace transform of the heavy side is 1 over s. Alrighty, let's move to the next function. Alright, let's do the round function. What is the round function? The round function is this one that I have here. So it's a function that on the negatives is 0, and on the positives is a straight line with slope 1. And then you see it's t times the heavy side of t, so 0 for the left. Remember that the Laplace transform will be the same whether this is t or t heavy side. But also remember that we're going to assume that our functions are causal. We're going to assume that our functions, the functions of t that we're going to solve for, there's some time that we call time equals 0. It's arbitrary, whatever is our origin of times, then is when things start. So before that, there's nothing in a way, the function is 0. So you see the Laplace transform of t, or the t, or the Laplace transform of t times heavy side t, which is the same, of course, because again, the Laplace transform ignores what happens in the negative domain. All right, so we are substituting the definition of the Laplace transform, and we have minus e to the minus st, and then f of t is t heavy side t dt. Now, of course, this is the same because the heavy side is 1 for positive domain of t, 0 to infinity of e to the minus st t dt. Now, this integral is best done with Feynman's trick, but I know that you're less used to that one than by parts, so I'll do by parts here. One of the very few cases that I'll do the integral. Most of the times I'm going to tell you that's the result of the integral, do it yourself, but this one is simple enough. So let's do it. It's not so cumbersome. U equals t, which means du equals dt. And we do dv equals e to the minus st dt, which means that v is equal to minus 1 over s e to the minus st. All right, so we do u times v. This is t time or minus, and put the minus first, e to the minus st divided by s from 0 to infinity. So let's write it like t equals 0 to t to infinity. Okay, and then minus the integral of v du. So what we get is v. We write the integral v du here. So we get 1 over the minus, and the minus makes a plus. I get a 1 over s. All right, and then I get the 1 over s, the integral of e minus st, which is from here, and then du, which is dt, and this is from 0 to infinity. All right, wonderful. So this integral, we got this. By the way, let's do this one first. What happens when t goes to infinity? This is the exponential of minus, if s is positive, which is the domain we're going to solve for, this thing goes to 0. The exponential, when t goes to positive infinity, is killing the expression. Exponential of minus something positive infinity goes to 0. And when t is 0, on the other side of the limit, that's also 0 because it's multiplied by t. So this thing does not contribute, all right? And we're left just with that. And what is this integral like? So this is the integral gives me a minus 1 over s, right? So I get minus 1 over s squared, and then the exponential of minus st evaluated from 0 to infinity, right? Now, with t, this is t going to 0 to infinity, from 0 to infinity. Now, this is minus 1 over s squared multiplied, and infinity is this thing goes to 0, so 0, minus at 0 it goes to 1. So we got it. The Laplace transform of t, or if you want, same thing as the Laplace transform of t, heavy side t, it's equal to 1 over s squared. And there we go. That's the solution. Important, s has to be larger than 0 for this to converge. And the reason is because we want this, when t goes to infinity, this needs not to diverge, right? Again, this is not so important. The convergence is s positive. So for the Laplace transform of t, the domain of the Laplace transform, capital F of t, capital F of s, if let's say, if f of t is equal to t, then capital F of s equals to the Laplace transform of t, is only well defined for s larger than 0. All right? Wonderful. All right. Now that we know how to transform t, let's check another function. All right, so the Laplace transform of the exponential function is actually really easy. Let's substitute in the definition, 0 to infinity, e to the minus st, f of t here is the exponential, so e to the kt dt, right? And then we realize that we can actually write this as the exponential of minus s minus k times t dt, all right? And let me call this thing s prime. If I call this thing s prime, all right, maybe I'll do it on top, not to clutter it. So if I call this thing s prime, so s prime is equal to s minus k, all right? Then what I got is that this is equal to the integral from 0 to infinity, e to the minus s prime t dt. And we have done this integral before. Exactly the same integral. The only difference is the same integral we've done twice already. The only difference is that now it's called s prime. So in the past, the result of this integral was when we did a transform of a constant. Remember the transform of 1? It was 1 over s, now it's 1 over s prime. So if we undo, and of course this is only valid if s prime is larger than 0. If we undo the change of variables, we get that the Laplace transform of the exponential function is indeed 1 over s minus k. I'm doing substituting s prime by s minus k. And of course, the convergence of that, the convergence of the Laplace transform in this case is s. So if we write s prime larger than 0, that means s minus k larger than 0. So that means that s has to be larger than k for this to be convergent. So in this case, the Laplace transform is not defined from s's that are smaller than k. But again, this is not that important for this course. I'm adding it here for completeness. Right? This is what you need to remember. That's what is important and what will be important for our purposes. The Laplace transform of the exponential is 1 over s minus k. Again, remembering that the Laplace transform of the Laplace transform of the exponential times the heavy side is also the same as the Laplace transform of e to the kt. We've been careful with that. We're not going to be that much literal in the sense that we're going to assume always that when we do inverses, for example, if we do the inverse of 1 over s, that would be constant, right? We will write the constant, okay? And when we do the inverse of, let's say, 1 over s squared, that would be t. So of course it will be constant heavy side or t heavy side. But if we understand what we mean when we say that, I think it will be fine. We will be able to write it like this. So we're gonna no longer write the heavy side everywhere unless we need it, okay? For convenience of the notation, for being quick. All right, so we learned how to do the Laplace transform of the exponential. Now, interesting enough, when s is equal to 0, is the Laplace transform of 1, no? Sorry, when k is equal to 0, the Laplace transform of e to the 0t, it's equal to 1 over s minus 0, so 1 over s. You see, the same as the constant. The Laplace transform of the constant is 1 over s. The inverse Laplace transform of 1 over s is the constant. So, the inverse Laplace transform of 1 s minus k is going to be the exponential of kt. Alright, just taking inverse Laplace transform on both sides. And the inverse Laplace cancels the Laplace. Alright. Okay, let's do sine and cosine. Alright, so let's do the Laplace transform of the cosine of at and the sine of at. Now, of course, you can do those with the definition, and it's not difficult. It will be an integral by parts, and it's actually not a difficult one. You've done it, exponential times the trigonometric, but this one is actually really easy remembering this. If you remember this, we know that we can extend this to the complex plane and say, right, the Laplace transform now of e to the I at, what is it? Well, I know what that is because the Laplace transform of the exponential is this, so now k is ia. So if k is ia, then I get 1 over s minus ia. All right, that thing I can write it in as I can multiply by the conjugate, numerator and denominator, and I get s divided by s squared plus a plus I a s squared plus a squared, sorry, plus a squared. All right, this is just multiplied by the conjugate. I multiply by s plus ia. If I multiply the denominator, I get s squared plus a squared, and the numerator becomes s plus ia, and I divide it into fractions. Right. How has that solved my problem? Well, it has solved your problem because you know that this is equal to the Laplace transform of cosine of at plus I sine of at, right? That's the complex exponential. And that means that's equal to s squared plus a plus I s squared plus a squared. Okay. Right, so I know that these two things are equal. So, and I just wrote this, the same thing. Wonderful. So then I can, the Laplace transform is linear. So I know that this is the Laplace transform of the cosine of at plus the I comes out, I Laplace transform of the sine of at. Right. And now we can say, okay, so, right, I can equate the real part on the right to the real part on the left. I can equate the imaginary part on the left, on the right, to the real part, to the imaginary part on the left, right? So if I do that, I get real part. On the left, the real part is, well, on the right first, the real part is, on the right, we get L, Laplace transform, the cosine of AT, and on the other side, I get S divided by S squared plus A squared. And then the imaginary part, I get that L sine of AT is equal to A divided by S squared plus A squared. There you go. And we have solved it. You can actually get these expressions doing integration by parts with definition. Please do it. It's good practice. One thing that you can wonder, if you wonder about the convergence of the Laplace transform and so on, is like, you said that the convergence for that one required that S is larger than K. How does that work in this case? Well, you just need that S is larger than the real part of this number, and it's purely imaginary, so it works always. The convergence for this actually is S larger than 0. If to get the convergence, you can do the integrals and see it, that's what you need. Or if not, if you want to get more information about the convergence and why in this case works, when K is imaginary, then come to let's discuss it in person, because it's kind of a cool discussion on a little bit of complex variables. It's beyond the scope of the course, but I'm so happy to discuss it. Basically, if you have an integral of something that is, let's say, AT plus, times e to the I bt, something like that, and then you get dt here, and 0 to infinity. What you need for it to converge is, minus AT. What you need for this to converge is, this is convergent if A is larger than 0. So it's the real part. And how do you see it? Well, do the integral, and you'll see it. That this thing, when you take limits, the exponential kills the contribution at infinity only when A is positive. That's why the radius of convergence of this one is, so the convergence of the Laplace transform for this is that when it's larger than 0. So it's better than the exponential alone. Anyway, different discussion for a different episode if you want, for the in-person sessions that we will have. The important thing to remember is what we just computed, that the Laplace transform of the cosine of AT is S over S squared plus A squared, and the Laplace transform of the sine of AT is A over S squared plus A squared. Now, let me quickly erase, by the way, please do it with the definition and integration by parts, it's good practice. And let me erase and write something really interesting. All right, so the interesting bit that I promised is that we quickly know how to invert the Laplace transform for these functions. The Laplace transform of S over S squared plus A squared is going to be the cosine of AT. That's typically something that I would ask you, what is the inverse Laplace? And you will look at that and tell me cosine of AT. Now, the inverse Laplace transform of A over S squared plus A squared is the sine of AT. What did I do? Well, just take inverse Laplace transform of both sides. Just let me do it. I know you will know, but let me do it with the cosine. With the cosine in here, I took inverse Laplace of Laplace cosine AT equals inverse Laplace of S squared plus A squared. Now, the inverse of the Laplace is the function. If I do Laplace and then inverse Laplace, I get the function back. And then this thing is L minus 1, the same thing. S over S squared plus A squared. And that's what I did in there. All right? Okay, let's see the next thing. I cannot snap easily now, so I'll do it with the board. Right? Let's see if the magic works. All right, so now that we've learned how to do the Laplace transforms of basic functions, let's study some properties that will be really useful for our course. The first one, very important one, is what we call the shift theorem. The shift theorem tells you that the Laplace transform of a function times the exponential is the Laplace transform of the function translated to the right by the amount in the exponent of the exponential. Remember, f of capital F of S is the notation for the Laplace transform of f of t. This is going to be super useful, and well, it's a theorem. Remember, theorems, you don't have to believe them. We can prove them. Let's do the proof. So, we have here on the left the exponential of kt f of t. All right, so to prove it, let's plug in the definition. The definition of the Laplace transform is minus st. Now put the function in there, e to the kt f of t dt. And we've done that already for the heavy side, so it should be very easy. So 0 to infinity, e, I group the two together, minus s minus k times t f of t dt, right? And then I call this guy, as I did before, s prime, s prime, all right? And then that means that this thing is going to be, the Laplace transform, let me just write it, the Laplace of 0 to infinity exponential of minus s prime of t f of t dt, and that is capital F of s prime, is the Laplace transform, right? Then we undo the change of variables here, and we get f of s minus k, and this proves the theorem, okay? So important theorem, and you have the proof. This is the proof. All right, wonderful. Let's prove another important theorem. All right, so this is called the derivative of the transform, because it tells you if you take derivatives of the transform, what is the inverse of, what is the function it comes from. So, or another way of reading it is, okay, what is the transform of a function multiplied by t to the power of n? And this is interesting, right? It tells you that this is minus 1 to the power of n, nth derivative of the transform with respect to s, the variable of the transform. Let's prove this theorem. This proof requires us to operate iteratively. So, first, let's consider what we want to obtain, t to the n times f of t, and then we substitute it in the definition of the Laplace transform. So this is the integral 0 to infinity, e to the minus st times t to the n f of t dt. All right? Okay. Now, the first thing that we realize is that, hold on, I can write, look at this. I realize of this, the derivative of e to the minus st with respect to s, and if I add a minus here, this derivative, it's equal to, that takes at minus t down, the minus cancels, is equals to t e to the minus st, right? So let's realize of that. So if I write here, the minus derivative, let's write it, minus d ds of e to the minus st, and then I want to write this in an equal sign. I cannot just write an equal sign because this is not exactly equal, e to the minus st is not exactly equal to that, but it's exactly equal to t times that. So that means that I can take one of these t's, so I get t to the n minus 1 f of t dt. And this is correct, right? If I substitute this by what I told you it was in here, if I substitute this by t e to the minus st, well, the t times t n minus 1 gives me t to the n, and the e minus st gives me that. So I've done nothing by writing that. I did a little bit like Feynman's trick. I took a derivative under the integral sign, but that's fine. Again, this integral is with respect to t, the derivative and this integral, they don't talk. They're different parameters. All right, hopefully you see what I did here. Now, because again, the integral is with respect to t and the derivative is with respect to s, and they don't talk, and the integral is continuous, I can take the derivative out of the integral sign, and it gives me minus 1. I'm going to write it like that. This is this minus sign, and then d ds integral from 0 to infinity e to the minus st t n minus 1 f of t dt. Wonderful. So look at that. I started. So this is actually this thing. If you identify here, this thing here, is the Laplace transform of whatever is here. So of t n minus 1 f of t. Oh, wonderful. So I went from the Laplace transform of t to the n times f to the Laplace transform of t to the n minus 1 times f. If I repeat this n times, I'm gonna remove the t from there, right? Because it's gonna be reducing. If I do it again, I'm gonna reduce the degree by 1 until I get to t to the 0. So let's do it. Let me just write for clarity those brackets there, and let's do that again. So let's do it a second time. I'm gonna do it a second time. I'm gonna use this identity a second time. Okay. I also have it here. So this is equal to, let me just write it, equal to, and then I write the minus 1 that I have there, dds, and then I write here, integral from 0 to infinity, and now I do the same thing again, this thing, minus d, ds, e to the minus st. Right. I have tn minus 1, and this gives me an extra t, right? This is this thing. So that to be the same, to be equal to that, I need to write t n minus 2 f of t dt. All right. Now, what do I do? Well, same as before, I take the sign out. So if I take the sign out, it would be minus and minus is plus, but let me keep track of how many times I've done it. Minus 1 squared. I take the derivative out, that is a second derivative, right? And then what I'm left with is the integral from 0 to infinity of e to the minus st t n minus 2 f of t. Right. And this is, of course, the Laplace transform of t n minus 2 f of t. All right. So we see how we do it, right? We do it a third time. If we do it, this is very easy to see what's going on. If I do it a third time, it would be minus 1 to the third, d cubed, ds cubed, integral 0, infinity, e minus st, t n minus 3 f of t, right? And then I can do it n times until I finish. I'm going to erase this. And if I do it n times, I get minus 1 to the power of n, dn ds n times, and that operating on the integral of e minus st. Since I've done it n times, I run out of polynomial here. There's no more t, it's t to the 0. So it's just f of t. And of course, the limits are 0 to infinity. Right, and if you realize this is exactly the Laplace transform of f of t. This is the Laplace transform of f of t. This thing here. All right, so that means that minus 1 to the n is the nth derivative. Sorry, minus 1 to the n times the nth derivative with respect to s of capital F of s, which is the Laplace transform of f. And this proves the theorem. All right? Hopefully easy enough to follow. If not, please do keep your questions and ask them in the review sessions that we will have. All right, very important theorem. Let's prove another very important theorem. Okay, here's another very important theorem. This theorem, we call it the transform of the derivative. Why is that? Because it tells you how to transform the derivative. Remember the notation? This is the same as saying the Laplace transform of the nth derivative with respect to t of f of t, right? Remember the notation we use, the nth derivative. So the Laplace transform of the derivative is s to the power of n, then the transform, remember f of s is the notation we use for the Laplace transform of f of t, all right? So it's s to the power n, Laplace transform of f, minus s n minus 1 for f, not the transform, the original f at time 0, minus s to the n minus 2 f of times 0 minus f, this is f dot, remember this is the first derivative, and f, no s's, right, multiplying f n minus 1 derivative. To understand this formula, let's write a particular case or two. So if I have the Laplace transform of the second derivative of x here is a function of t, right? So this thing would be, all right, n is 2 in this case, so it's s squared. Then capital X, let me notate the capitals like that, of s. Capital X is the Laplace transform of x minus s minus n minus 1, that is s to the power of 1. And this would be x, small x at 0. And the next one would be nothing to the n minus 1 derivative. So this one would be minus nothing x dot of 0. All right? Again, if we were to do, let's say, I don't know, the third derivative of y, why not? Let's do that one. So the Laplace transform of the third derivative of y is s cubed capital Y s minus s squared small y at 0 minus s y dot at 0 minus y dot dot at 0. Alright, so hopefully this formula makes sense with a couple of examples that I give. So, every time that you have some derivative of the function, it's very easy to transform in terms of the function and initial conditions. You see, those are x when t is 0. Those are initial conditions. So this is going to be really, really good for solving differential equations. Crucial theorem. This theorem is crucial. Now, it would be very sad if you have to believe it, because I told you. Sometimes it'll have to happen and you have to trust me, I guess. But not this time. This time, even if I'm an imposter, I'm not your professor for some reason, you will be able to believe and use this theorem, regardless of that, because you can prove it yourselves. Let's do the proof. All right, let me erase this quickly. All right, for the proof, we're going to proceed, same as before, iteratively, okay? So let's first prove the case Laplace transform of x dot, right? Which, or f of t is what we call it, right? So f dot of t here. And that case will give me, okay, remember, s to the power of n, in this case this is s times capital F of s minus f of 0 in this case. All right, so let's prove that case first. Then I'm gonna actually, for the proof, I'm gonna do one case and we will see how it generalizes. All right, so L of f dot of t, if I write the definition, I get e to the minus st f dot of t dt. Now, of course, this proof is kind of asking for integration by parts. Why? Because I want to have on the other side capital F. Capital F will be the Laplace transform of f, not of f dot. But you know, there's a trick that takes derivative from here and puts them here. When you have a product, taking the derivative of this and put it here is precisely what integration by parts do. So let's do integration by parts. Let me call this, this thing is u, and this thing, I call it dv. All right? Now it's very easy, right? Because that means that du, it's equal to minus s, right? Sorry, my bad. du, it's equal to minus s e to the minus st dt, and v is just f of t, it's the integral of dv. All right, so let's substitute that. So here we have u times v, so it would be e to the minus st times f of t. All right, this is evaluated between 0 and infinity. Okay, that's fine. Minus the integral between 0 and infinity of v du. So let's write this. So v is f of t, and then du is minus s e to the minus st dt. All right, next step. What happens at infinity? At infinity, when this is t going to infinity, this will kill the function. So you see, this function has to be regular enough. That's when I always say regular enough, so that it's killed by an exponential at infinity. So this function cannot be growing faster than an exponential. It could be anything, but something that cannot grow faster than the exponential of st. It could be an exponential itself, but then it will reduce the convergence of the Laplace transform, if you remember what we saw when we transformed the exponential. But again, those are more advanced points that we can discuss in our review sections. For now, assuming that the exponential dominates this function, so when s goes to infinity, this is killed. And when it's 0, this is 1, the exponential. So basically, the first term becomes f, let me just write it out. So f of 0, well, if you want, I can write it, right? It's at infinity, let me just write it. So it's the limit when t goes to infinity of e to the minus st f of t, that's the upper limit, and then the lower limit minus e to the 0 f to the 0. All right, this is this valuation, and this thing cancels. All right, and this thing just becomes minus f to the 0. Anyway, and then minus, and then remember the s can come out of the integral because this is an integral with respect to t, not with respect to s. In fact, s is the only variable here. Remember, t is a dummy variable, it's integrated. So s comes out. So if it comes out, it's a minus s and a minus here, so it's going to be a plus s integral from 0 to infinity of e to the minus st f of t dt. All right, cool. So let's recap what we have here. This thing here is just f of 0, well, minus f of 0 if we include the sign. And this thing here is precisely the definition of the Laplace transform of f of t. So this thing is f of s. All right, so if we substitute, we get equal, substituting here. So it's, I'm going to reorder, I'm going to write this one first. S times f of s, this is this, and I'm going to write this here now, minus f of 0. And there we go. We prove it. That's exactly what we wanted to prove. All right. Now, I'm not going to do the second derivative, third derivative. You're going to do it. But you can quickly see, if you have two derivatives, what you do is integration by parts twice. You do it once, and here you will end up with a dot. And then when you end up with a dot, it's the Laplace of the first derivative, and then you substitute again this, and you end up with all the series of terms that we have here. Please do it. It's very easy. All right? Okay, so this is a very important theorem, the transform of the derivative, one that we will use quite a lot to solve exercises. All right? All right, let's do another one. By the way, if you want to do the second, of course, what you have to prove, I'll write it again here, even though you had it before. Prove now that f dot dot of t, Laplace transform, right, is, what would it be? Well, it would be s squared f of s minus s f of 0 minus f dot of 0. That's what you have to prove. And then you do it a third time, and you get extra, you'll see the pattern very easily. In fact, you can even see it now. This one will take out, if there's a dot in here, because you start with the second derivative, you will end up with a dot in here. And when you do integration by parts here, you're going to get the s that multiplies here, and then the exponential of 0 f of 0 again. So easy to do it, but please do it. Until you do it once, it won't look so easy. Huh? So please do it. All right, yeah, let's see another theorem. All right, so another theorem is the Laplace transform of the integral. The Laplace transform of an integral from 0 to t of f of t is 1 over s Laplace transform of f of t. Now, this one is actually easy to prove if we use the theorem that we just proved before. Let's write before something that we know. We know from before that the Laplace transform, the Laplace transform of the derivative, let's just write it like that, the Laplace transform of the derivative of some function g of t, first derivative, it's equal to s capital G of s, the Laplace transform of g, minus small g of 0. All right? That we know from before. All right. Now, let me define, to prove this, let's define a function g of t that I define as that, the integral from 0 to t, f of t dt. Now here, t is a Lamy variable of integration, but it's also in the limit, and that's why the whole thing depends on t, because it's in the limit, okay? If I write a number 9, it no longer depends on t anymore. It's because I write a t here. In fact, if we are rigorous about it, we should write primes here, not to repeat the same. It doesn't matter, we use it all the time, okay? But if we are a little bit rigorous, we don't call this variable, the dummy variable, the same as the limit. But it doesn't matter. You see, it's super important. It's so irrelevant. I could call this one Joshua, and it would be exactly the same. When you integrate this as a function of Joshua, and then you evaluate at the limits. All right. Anyway, so we define a function like that. Oh, let me just write explicitly. This is the same 0 to t f t dt is the same as 0 to t f of Joshua. The Joshua. Okay, is that clear? It's the same. All right, I'm not going to erase that because I mean it. Anyway, so g of t, right? Again, it's equal to integral 0 to t f of t dt. Very good. Now, that means if I take derivative with respect to t of this, the derivative cancels the integral, fundamental theorem of calculus that you saw last year, and that means that this is exactly f of t. All right, wonderful. Now, that means that the Laplace transform of g dot, taking Laplace transform on both sides, it's equal to the Laplace transform of f of t. Right? All right. So, this is f of s. Okay? Good. So, that means that capital G, so let's just use this. Now we use the theorem that we proved before for the first derivative, and s, capital G of s, minus g of 0 equals capital F of s. Right? We use the theorem that we proved before here. Right, by g of 0, we know how much that is. If we substitute in the definition, g of 0 is the integral from 0 to 0 of f t dt. G of 0 is 0. This implies that g of 0, which is again the integral from 0 to 0, f of t dt, is exactly equal to 0. Then we get that s of g times gs is equal to f of s. And that means that g of s is equal to 1 over s f of s. But what is g of s? Well, g is the Laplace transform, capital G of s is the Laplace transform of small g of t. And small g of t, so this thing is equal to the Laplace transform of g of t. But if we substitute g of t, this is the Laplace transform of the integral from 0 to t f of t dt, by definition of g of t. All right, so that means finally that the Laplace transform of 0 to t f of t dt is equal to 1 over s f of s, which is exactly the theorem we wanted to prove. All right. Again, notice that I could call this anything. I know some of you would be shocked and go, oh, hold on, what? but I want to expose you. If I do, this is a side note. Just take this is the theorem as we got it, with or without the primes, I don't care. If I write here f of x dx, it's exactly the same thing, because this whole thing is a function of, this is a g of t. The x is not there, it's a dummy variable, it's summed over. Well, it depends on t because of the limit, okay? Alright, please get that in your mind. I know that this is usually something that second year ECE students struggle with in my past experience. So if you have questions about it, you feel it's outrageous, right, wonderful. I want to outrage you and then come to talk to me and we will discuss it, alright? Alright, wonderful. Let's see more interesting theorems. Alright, so we're going to see something called the second shift theorem, but before that, we're going to see a couple more things. Now first, these ones we've already seen. This is the first shift theorem, if you remember. The Laplace transform of the exponential times a function is the function shifted to the Laplace transform of the function alone. Remember, capital F is the Laplace transform of small f, shifted to the right by an amount k. And we also saw that the Laplace transform of the heavy side, which is the same as the Laplace transform of 1, is 1 over s. Now, I'm going to write another quick theorem that we're going to prove first. That is the following. The Laplace transform of displaced heavy side, t minus a, it's equal to e to the minus sa divided by s. All right. So how do I prove that one? You see, that looks a lot like it's very similar in a way to this, but kind of reversed. How do we prove that one? This is I'm gonna square it because it's a little theorem that we haven't proved. Let's prove it for a second. Let's call it 1. So proof of 1. All right, that's not very difficult. Again, remember that theta of t minus a, all right, is just to remind you, is 0 when t is less than a, and 1 when t is larger or equal than a, all right, because it's a heavy side displaced to the right by 8 units. All right, so to prove that one, let's just use the definition, very easy. Theta t minus a, it's equal to, inserting the definition, 0 to infinity. Then I have the theta t minus, well, I'll write the e first, because that's what we've been doing. E to the minus st, theta t minus a, dt. All right, so this is easy because this thing from 0, you can split it. I'll do it with full steps. You can split this integral in two. One that goes from 0 to a, e to the minus st theta t minus a dt, and another one that goes from a to infinity, e to the minus st theta t minus a dt. Now, between 0 and a, this is 0, so that cancels. The only one that survives is this one, and between a and infinity, the heavy side is just 1. So this is equal to the integral from a to infinity of e to the minus st dt. All right, so let's integrate this this little thing here, and that integral we get is the integral of the exponential. So it's the integral of 1 over s, so if you want minus 1 over s, minus 1 over s, right? E to the minus st from t equals 0 to infinity. Right. So we substitute and we get minus 1 over s. Now, what happens at infinity? Well, at infinity, this is killed by the exponential. So at infinity, we get a 0 minus, a. I wrote a 0 in here, my bad. T equals a to infinity, okay? So at infinity, the exponential cancels, and at a is just the exponential. So it's e to the minus sa. right? Which is equal to 1 over s e to the minus sa, which is theorem 1, which is what I wanted to prove. Okay? So that wasn't too difficult. Let's go again. So now that we proved that little theorem that is helpful, let's prove something a bit more general. This one, the second shift theorem. You can tell that this is, if you want a particular case, sorry, this is a general case of that one, because when f is equal to 1, you get what I call theorem 1. Theorem 1 is a particular case of the second shift theorem. I did it first because the proof of this is going to be very similar. All right, so let's prove it. You see, I have the second shift theorem written in two ways. The direct form that we're going to prove, and this is the inverse form. This is the one that we're going to use the most. You see what I did? From here to here, I took inverse Laplace transform on both sides of the equality. So the inverse Laplace transform of e to the minus sa capital F of s is heavy side t minus a, f of t minus a. Okay? This is the way we're going to use it to solve differential equations. All right, so let's prove the theorem. So, Laplace transform of theta t minus a, f t minus a. Wonderful. Let's introduce the definition here. So it's from 0 to infinity of e minus st f, well, I write the heavy side first, heavy side of t minus a, f of t minus a, dt. Same as before, I can split this integral in one integral from 0 to a, that is 0, because the heavy side is 0 then, and then the integral where the heavy side is 1 from a to infinity. So this is the same as we did before, from a to infinity, e to the minus st, the theta is 1 in that case, f t minus a dt. All right? Now, for this, we do a change of variables. So change of variables, substitution as you call it, change of variables. I'm going to define a variable t prime equals t minus a, which means that t is equal to t prime plus a. All right, super important. Now, when we do a change of variables, we also need to change the integration limits. When t is infinity, t prime is also infinity because it's t minus a. So infinity minus a, infinity. When t prime is a, when t is a, t prime is 0. So right, so when we change variables, we need to change the limits. Wonderful. So we get, in this case, there we go, yeah. T in here goes to the exponential of s minus s t prime plus a, okay? And the f goes, t minus a goes just directly, t is t prime plus a, so this is just t prime dt prime. All right, wonderful. Now notice, exponential of minus s a can come out of the integral, because the integral is with respect to t, not with respect to s or respect to a. So, wormhole opening, and then we get this is equal to e to the minus sa, integral from 0 to infinity, e to the minus st, f prime, f of t prime, dt prime. And this thing is the Laplace transform. This thing is the Laplace transform of f of t, which is the same as capital F of s. Now, importantly, typical question, by the way, if that is the case, I've already proven it, because this is e to the minus sa capital F of s, which is the right hand side. Start at the left hand side, I finish with the right hand side, and this is proven. Now, question that I typically get when I say things like that to ECE 205, and that's why I insist so much on dummy variables. No, right? You need to undo the change of variables back, no? This is not the Laplace transform of f of t. I'm quoting the question. The question is not a good one, but I'm quoting it as if, I mean, it's actually a good question. What I mean is not correct what the question is saying. That's why I quote it. So, some people who will see this would say, No, right? This is the Laplace transform of f of t prime. And you would have to undo the change of variables in order to get the result. And again, no. This is the Laplace transform of f of t, or f of Joshua. This thing, t prime, is not a real variable. It's a dummy variable. It's a placeholder telling you to sum over all the possible values of t prime. If I do another change of variable, would you be happy if I tell you, no, now change to a new variable, t prime equals t? Or I don't know, Joseph, like that, right? And then I write Joseph here, Joseph, Joseph. It's exactly the same thing. So no, this is not the Laplace transform of f of t prime, or actually it is, but it's the same as the Laplace transform of f of t. There is no dependence on t in the Laplace transform. The Laplace transform depends on s, not on t. T is a dummy variable, all right? If that is not clear to you, please bring the question up in our sessions, because I look forward. It's really a good question. I said it's not a good question. What I meant to say is it's not correct, the claim. No, this is not different from t prime or anything else. It's the same. This is equal, again, integral of f of t dt is exactly equal with a and b. Is exactly equal to integral f of t prime dt with the same limits. It's exactly equal to the integral of f Joshua d Joshua with the same limits, okay? In all these cases, it's the same integral. It does not depend, that integral is a function of a and b, but not a function of t, or any of these are dummy variables. So please think about it, convince yourself, and if you don't convince yourself, ask me the question. This is something I get every year, and I have to try to anticipate because this is on video, okay? So yeah, no, this is not the Laplace transform of f prime, it's the Laplace transform of f of t. Not the Laplace transform of f of t prime. Or actually, a better answer is yes, it is also the Laplace transform of f of t prime. It's the same. This is a placeholder, a dummy variable. The Laplace transform of a function of t does not depend on t. All right, hopefully that's clear. If not, please bring it up. All right, so we proved the second shift theorem, and this is the most important form of the second shift theorem. What we're gonna do to finish this video is we're gonna actually apply things that we've learned to solving a differential equation before getting into more complicated things. The next thing we're gonna see is the Dirac delta function, also called in engineering often the impulse function, and that is exciting, and I promise to you it's exciting. But before that, let's see in practice how to solve a differential equation with Laplace transforms with things that we've learned. Let me erase the board. Alright, so we're gonna solve this IVP, remember, initial value problem, a differential equation. I don't want the general solution, I want the particular solution that satisfies x of 0 equals 1, x dot of 0 equals 0. Remember, it's a second order equation, so I need two constants. So I need to find the value of two constants, so you need two initial conditions. Now, of course, you will know this one is not very difficult to solve with the methods that you know how to solve. In fact, you will find the characteristic polynomial for this. Why don't we do it like that first? Let's do it first with the methods that we know, and then we will do it with the Laplace transform to compare, okay? The Laplace transform is more powerful because it will be able to solve non-constant coefficients, for example, very easily. But for now, let's do it with this equation that we can solve with our old methods. If we were to solve it with the old methods, right, we will find the characteristic. Well, old, but it's the one you would use in an exam. If you just ask solve this, you could choose which one. We could do the Laplace transform of the methods in the previous videos. This one you choose. We will see which one is easier. But there will be others that you will have to use Laplace transform, okay? Characteristic polynomial. So in this case, the characteristic polynomial is lambda squared minus lambda minus 2. All right, so roots. Okay, lambda is equal to minus b, which is minus 1, plus minus the square root of b squared, so 2, so 1, minus 4 times 2, which is 8, plus 8, because it's a minus, it's minus minus, divided by 2. All right, so that's easy, because this is 9, is 1 plus minus 3, divided by 2. So you get lambda 1 equals 2, and lambda 2 equals minus 1. All right? So you get two eigenvalues, which are two real roots. Two simple real roots. All right, so with two simple real roots, we know that the solution is C1 e to the 2t plus C2 e to the minus t. And we also need the derivative to impose the, remember, we need to find these two constants to satisfy the two initial conditions. It's not enough to give that for an IVP. We need to find the exact value of the constants to satisfy those initial conditions. And we need a derivative, therefore. So x dot, it's equal to 2c1 e to the 2t plus minus c2 e to the minus t. All right, let's impose the initial conditions. So we impose x of 0 equals, let's do x dot of 0 equals 0 first. That's going to be easier. So if we impose that one, we get that twice c1 times 1 minus c2 equals 0. So that tells me that c2 is equal to twice c1. All right, let's impose now the other one. The other one tells me that x of 0 equals 1, and that means that x of 0 equals 1 means that c1 plus c2 equals 1. Now I substitute c2 is twice c1. That means that c2 is twice c1, so I have 3c1 equals 1, which means that c1 is 1 over 3. And then c2 and c2 is equal twice c1, so 2 over 3. Finally, the solution is 1/3 e to the 2t plus 2/3 e to the minus t. All right, so that's the solution. And that would be, using the old method that we learned, the solution. Let's solve this equation now using the Laplace transform. Let me move this here and erase the rest of the board. All right, so I move myself here, I move the equation, the solution over there, I store it there so we can take a look and compare when we finish with the other method. Now, it took a while to impose the conditions. Just imagine that we will have to impose those conditions when we have inhomogeneities and when, you know, and sines multiplying polynomials and cosines. It becomes really cumbersome. Easy, but cumbersome to impose those conditions and solve the equations. The Laplace transform comes with everything built in. So we don't have to impose all these things. We will see. Again, keep in mind this is the simplest ever case, but an IVP with initial conditions. All right, let's go ahead. So how do we solve this with the Laplace transform? Well, what we do is the Laplace transform of both sides of the equality. So let's Laplace transform both sides of the equality. All right. So the Laplace, so I'll write the steps. I Laplace transform the equation, Laplace x dot dot minus x dot minus 2x equals Laplace of 0. Now the Laplace of 0 is 0. Put the definition inside the integral. The integral of 0 is 0. And the Laplace is linear, which means that I have the Laplace of x dot dot minus the Laplace of x dot, all right, minus 2 Laplace of x, all right, equals to 0. All right, now I know these theorems that I have here. I know that the Laplace of x I'm going to call capital X. I'll do serifas for the capital X of S. This is capital X of S, okay? So I'm going to write the transform using the theorems. All right, so we have, after the linearity of the Laplace transform, I wrote in blue here the different terms, and we're going to write what every one of them are. So this is the Laplace transform of the second derivative of S. The formula is here, so let's apply it. This thing is S squared, capital X of S, which is the Laplace transform, minus S of small x of 0, minus x dot of 0. All right, you see? This is the Laplace transform of the second derivative. Now here we write the minus Laplace transform of the first derivative, that is here. So minus s capital X of s plus, because there's a minus here and a minus in front, x of 0. And then finally, minus 2, well, I've written here minus 2, capital X of s equals 0. All right, so we substitute the initial conditions that we have here. Look how easy it is to implement them. X of 0 is 1, so this one is going to be 1. This one is 0. This one is 0 as 1. So what we get, if I write it, let's just write it here. S squared capital X of s minus s minus 0. Then minus s capital X of s plus 1 minus 2 capital X of s equals 0. So we have this equation, and the unknown is the Laplace transform of x. So now let's solve for the Laplace transform of x. So we have what multiplies capital X. So I have an s squared minus s minus 2. Minus s minus 2. That multiplies capital X of s. And then I'll put on the other side the rest. And the other side we have a plus s minus 1. All right. So that means that capital X of s, it's equal to s minus 1 divided by s squared minus s minus 2. So that's nice. That's the solution in the S space, the S domain. Is the Laplace transform of the solution. You see, I found x of s. That's the Laplace transform of my solution. Now, interesting thing to note. What a coincidence. The denominator of this is the freaking characteristic polynomial, right? Remember? Lambda squared minus lambda minus 2, s squared minus s minus 2. Huh, what a coincidence. Perhaps it's not a coincidence. And maybe it's just one exercise. Let's keep our eyes open to see if we find that more often. For now, I don't know, it's just a coincidence perhaps. Alright. Anyway, said nothing. I don't know, cheeky. Kind of nerdy, in a nerdy way cheeky, but cheeky nevertheless. Alright. So, now what we have to do is undo the Laplace transform, right? This thing, remember, capital is the Laplace transform of x of t, and that's what we want, that's our solution. So that means that x of t would be equal to the inverse Laplace transform of capital X of s, right? So in other words, the x of t would be the inverse Laplace transform of s minus 1 divided by s squared minus s minus 2. So we need to invert the Laplace transform. And how do we do that? Well, we use, yes, we haven't used it yet, and there was a preliminary, we use simple fraction decomposition and the theorems that we have learned. And look, it's going to be really easy. Of course, it requires practice like everything, but once you practice once or twice, you're going to be like, oh yeah, this is super easy. Let's do it. Let me erase the board. All right, so we found that x of s, so the solution in the S domain, in the Laplace transform domain, if you want, the Laplace domain, is s minus 1 divided by s squared minus s minus 2. And I know that whatever the solution is, it would be x of t, the inverse Laplace transform of this capital X of s. Alright, so I need to find the inverse Laplace transform of that, as I said. Let's decompose this in simple fractions. It's actually easy because we already know the roots of this polynomial, because we already found the characteristic polynomial. So s minus 1 divided by s minus 2 times s plus 1. Those are the roots of the characteristic polynomial. Now notice that the s's and the 5's are easy to confuse with my handwriting. Remember, the same thing as I did in simple fraction decomposition. When I have a 5, I write it really big and with a serifa to make sure that this is 5s. You will be able to distinguish it. Huh? So if you are doubting if it's an s or a 5, it is an s. Because a 5 would be very explicit. So this is an s. Alright, s. Alright, so we decompose it in simple fractions. If you don't remember how to do it, now it's time to go to one of the first videos. That is the recalling the simple fraction decomposition, okay? Ideally, there would be a card somewhere there, but probably, probably not. I don't know. We'll see. All right. So this thing is a s minus 2 plus b s plus 1. All right. Wonderful. So we write this fraction is equal to, I'll write a wormhole here, and then incoming wormhole here. So this is, doing again the common denominator, I get a times s plus a plus bs minus 2b divided by s minus 2 s plus 1 equals to the original. So these two things are equal. All right. So that means the denominator is the same, so the numerators have to be equal. So that means that s plus a plus bs minus 2b equals s minus 1. All right. Now, all that we do now is equate all the powers of s on the left with all the powers of s, all the coefficients of s on the left with all the coefficients of s on the right, all the coefficients of s to the 0, the independent terms on the left equal to the independent terms on the right. So again, coefficients of s, we get on the left we have a plus b, and on the right we have 1. So a plus b equals 1. And then the coefficients, this is s to the 1 if you want, coefficients of s to the 0, the independent terms. I have on the left a minus 2b, and on the right minus 1 equals minus 1. So if I solve this system, that's an easy one, it's the same we had before. We get that a is equal to 1 over 3 and b is equal to 2 over 3. How suspicious. We'll see. All right, wonderful. So that means that capital X of S I can write as a, so 1 over 3 multiplied 1 over s minus 2 plus 2 over 3 multiplying 1 over s plus 1. All right. Now, that's x of s. Now, let's compute small x of t, the solution to my problem. So that's equal to the inverse Laplace transform of capital X of s, and that's equal to, because the Laplace transform is linear, 1/3 the inverse Laplace transform of 1 over s minus 2 plus 2/3 the inverse Laplace transform of 1 over s plus 1. But those inverse Laplace transforms I know, because I know that the Laplace transform of 1 over s minus k is the exponential of kt. Do inverse Laplace on both sides and you get the inverse Laplace transform of s minus k is the exponential of kt. So this inverse, I'll write it in blue. This inverse Laplace transform is the exponential. Remember, k in this case is 2, so exponential of 2t. And this one is the exponential of, remember, k here is minus 1, so this is the exponential of minus t. Agreed? Again, I use this expression, and this expression, if I invert the Laplace transform, I get Laplace inverse of Laplace of e of kt equals inverse Laplace of 1 over s minus k, right? Then the inverse and the Laplace cancel, so the inverse Laplace transform of 1 over s minus k is the exponential of kt, and that's what I use here. I'm going super slow, but hopefully that allows you to understand what I'm doing. If not, you know, you have to come. I'm looking forward to your questions in the in-person sessions. All right, wonderful. So finally, this is the solution. Let's recap. X of t is equal to 1/3 e to the 2t plus 2/3 e to the minus t, and that's the solution. And if we compare it with the one we obtained with the old method, it's exactly the same one, So we validate with this example that the method works and that our calculations are correct. All right, so now you've seen that the Laplace transform can be used to solve differential equations. Now you will tell me, for this one, I would have not done Laplace transform because you're less used to it. Once you get used to it, it's super fast and you don't have to deal with imposing the initial conditions and so on in a way that could be confusing. But anyways, for this one, that is super simple. It's a linear homogeneous of constant coefficients. Perhaps that one, you would have not done Laplace transform. Yeah, me neither, to be honest. Probably I would have solved it the other way as well. But this is going to get complicated, and we're going to go outside of the realm of things that you can use the old methods. We're going to go to cases where the coefficients are not constant and where the inhomogeneities are tough. For example, Heavisides or delta functions that we haven't even seen yet. So just wait for it, okay? But now at least see how to use the method. And hopefully, if you don't understand anything of what I've done, please do ask questions. Now, the next video will be about a little bit of distribution theory, a tiny bit. You're going to be seeing another glimpse to really advanced math that you need to know a little bit of to use it at user level, right? At user level. It's like, I'm going to show you a simple script in Excel, if you were, because you need it, but you're kind of taking a glimpse at coding a little bit. Very similar. You're going to take a little glimpse on at really advanced math, but it's going to be fun, honestly, because I'm going to introduce it to you the way that Dirac, first a physicist, by the way, mathematical physicist, the way Dirac introduced it. And it was introduced as if like he needed it, and I need something like that, and I'm going to do it, and it looks crazy, and all mathematicians looked at him and said, this is crazy. That said what I needed, and it kind of makes sense. And it took about 20 years to actually formalize it and make it work rigorously. I promise it will be fun. We're gonna do in one lecture 20 years of pure mathematics, but we're not gonna go, of course, to the depth that those pure mathematicians got. But I promise to you that's gonna be fun. It's the kind of thing that when I show you, you're gonna be like, what? No, that can't be. And with good reason, you'll be outraged. All right, so much for anticipating the next lecture. This is all for now. I'll see you in the next video.